Great. Okay, here we go. So this is our last class of the semester. It's kind of crazy that we're here already, but here we are. Here we are. So I'm going to use the time to go over some. Well, if there are no questions or no one has anything in particular that they would like to discuss, I will use the time that we have left to review some of the material that we haven't been tested on directly via assignments or quizzes. So mainly the last parts of the regression section that included categorical variables and working with categorical variables and some of the forward selection stuff. So to do that, my intention is to use the practice problems that I posted. One of the problems in particular is a problem that kind of incorporates all of that information within it. So it seems like a logical problem to use for what I would like to go over with you guys. But that being said, I'm more than willing to let you drive the section. So if there's something in particular that you would like to talk about, or there's a particular kind of problem that you would like to see, please let me know, because again, I don't have any issues with going over that material. But if not, I will, as I said, just use the time to work through some of this extra stuff that I had posted in the practice problems. So with that being said, does anyone have any questions for me? Can you please go over questions 2I and 3F? 2I and 3F from what? The practice problems? Okay. 2I. So 2 says the following data or the following table gives the percentage of investments in energy securities and tax efficiency for 10 randomly selected and independent mutual fund portfolios. Okay. Use the appropriate diagram below to propose a straight line model for the study of interest. Okay. State the assumptions. Do the assumptions appear to be met? 2E. Consider the table. Interpret the estimate. Does the interpretation have meaning? At the 5% level, is there evidence that the explanatory variable is useful? The standard errors were calculated for the prediction. Okay. For this data set, oh, this is a good one. Okay, yeah, we can do this. I like this one. Okay, so we need to start off just by kind of clarifying what's going on in question 2. Okay, so we have two variables, tax efficiency and energy securities, and both are measured in percentage. From the first plot here, which is a scatter plot of energy security versus tax efficiency, what we can see is that we are trying to model the security as a function of efficiency. So we have Y is energy securities. I'm recording, right? Yeah. Is energy securities. And we have X, and this is in percent, is tax efficiency, also in percent. Okay, so our linear model is going to be Y is equal to beta 0 plus beta 1X plus epsilon. Okay, now, in the first 4 problems, we're basically just setting up the analysis. So we're just saying, like, does it seem like we can use a linear model? Does it seem like normality and constant variance are intact? And does it look like there's any outliers? So these are all things that we've learned how to do from evaluating the plots. Very briefly, it's pretty clear that there's some the model assumptions are not really intact here. Like, you can clearly see from the normal probability plot that we have curvature. Now, you might flag this value as an outlier anyways, but this is still evidence of a non-linear relationship. It's pretty difficult to argue that that there isn't a curvature here with the way that the data is being distributed compared to the quantiles. And then here you can see this is not a random pattern. So this is an increasing relationship. Right? So this certainly doesn't show us what we would expect to see when we're looking for constant variance. So we definitely have some issues with the assumptions of this particular model. But moving ahead to the question of interest. So from E, we have a table that we can utilize to fit the model. So just for clarity here, the fitted model is going to be yi hat is equal to 80.803 minus 1.17 xi, all right? All right, now, in part I, we want to compute the regression ANOVA table for this model. All right, so we have the following. So every ANOVA table, we start with our source. We're going to have three sources here, which are the regression source, the error source, and the total. Then we will have our degrees of freedom. Then we will have our sum of square. Then we will have our mean square. And then we will have our F value. All right. So for all regression tables, the degrees of freedom and the sum of squares must add to the total. Okay, so we are fitting a simple linear regression model in this case. Oh, sorry, there's one other thing that, well, we'll come back to it in a minute. So whenever we are working with a simple linear regression model, the degrees of freedom for the regression source is basically just the number of explanatory variables in the model. So in this case, we only have one explanatory variable. So the DF for regression is going to be 1. Okay, because we only have one X, which is the tax efficiency. The total is always going to be n minus 1. Okay, so if we go back to the question, we are told that we have a total of 10 tax efficiencies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay, so that means that here we're going to have 9. And then the error DF is going to be the difference between these two values, which is 8. And this is the same thing you can see as n minus k minus 1. K is equal to 1, so 10 minus 1 minus 1 is equal to 8. Does that make sense? Okay. All right, what else do we know? Okay, so we're told little SE is 28.92. Right, and we are told the sum of yi squared (61892.49), and we are told the sum of yi is equal to 742.5. All right. Okay, so for starters, little SE, so let's just pull up our formula sheet here. Here we go. Okay, so you can see here in the formula sheet that we have a note that little SE is equal to the square root of SSE over n minus 2. Okay, so this is equal to the square root of the SSE over n minus 2 in the case of SLR. Okay, in general, this is the square root of SSE over n minus k minus 1. All right. So therefore, SE is actually just the square root of the MSE. So therefore, the MSE is equal to the little se squared. So this value here is going to be 28.92 squared, which is equal to 836.3664. Does that make sense? That's one of the sneakier parts, actually. That's probably the sneakiest part of the whole problem, I think. Okay. All right, now we can also get the SST because the SST is simply the sum of the yi squared minus the sum of the yi all squared over little n. So this is going to be 61,892.49 minus 742.5 squared divided by 10, which is equal to 6,761.865. All right. Okay, so from this point, all we have to do now is make use of the properties of the ANOVA table. Okay, so first of all, every mean square value is a sum square over its degree of freedom, right? So the MSE is equal to SSE divided by 8 for this particular problem. So to find the SSE, we can just take 8 and multiply it by 836.3664. And that gives us 6,690.931. Okay. Now to find the sum of square regression, we know that SS regression plus SS error must equal SS total. So therefore, SS regression is just the difference between the total and the error. So that's going to be 6,761.865 minus 6,690.931, which is 70.934. And then the mean square is the sum of square divided by the degrees of freedom. So this is just going to be 70.934. And then the F value is the mean square regression divided by the mean square error. Sorry, one sec. Which is going to be 0.08637. Okay, so sorry, one sec. I'll answer that in a minute, Ansa. Does that make sense to everyone else, how I filled out the table? Any questions about the completion of the table? Okay. Do we have to make our formulas like this if something is not given in the exam? Okay, if I'm understanding the question correctly, the answer that I would give you is there are many different ways to start an ANOVA table. In general, to get the degrees of freedom, you just have to know the sample size and the number of, and the model that you are working with. If you have sample size and the model, you can work degree of freedom out from just that information. The sum of squares and the mean squares can be found in a variety of ways. In this particular problem, I purposefully gave SE to test if you recognize the relationship between SE and the mean squared error. So this formula relating MSE and SE, this is a definition, so you can always use this. And then following from that, the definition of the SST is something that we also have established on a number of occasions, right? So the sum of square total, well, I don't actually have it here for the regression model on the formula sheet, but SS total is always the exact same thing. So well, here it's defined in terms of X's, but maybe I should put those in. Yeah, okay, so I'll add a table like this to the formula sheet for the regression model just so that you have it. Yeah, so I'll throw that part in there too because I don't have those exact definitions written down. Well, actually, you can see here too, SE square root of MSE. Anyways, sorry. So to answer the question, it really just depends on what you're given. The properties of the ANOVA table, so the fact that the degrees of freedom add to the total, that the sum of squares add to the total, that the mean square is always the sum of square over the degree of freedom, that is consistent across every single ANOVA table. But the relationship of the mean squared error to SE, that's a regression property. I don't know if that answers your question or not. Okay, cool. Okay, 3F. Okay, question 3. A simple random sample of 19 stock portfolios contain 2 explanatory variables, profit and type of industry, and 1 response, price to earning ratio. We have some information. Okay, so let's just start off by writing down the model that we have so that we know what we're working with here. So this is again a regression problem, but it's a multiple linear regression problem. So we have y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 plus beta 3 x3 plus beta 4 x1 x2 plus beta 5 x1 x3. Okay, so x1, or we'll start from the top. Okay, so y is the profit to margin ratio. So that's our response variable. X1 is the profit margin. Okay. X2 is a categorical variable. So it's representing the type of industry. So this has 3 levels: oil, health, electronics. So you can see that here we have health and here we have oil. What that means is the categorical variables both have reference levels of electronics. So X2 is going to have the following form. It's going to look something like this. Okay, so 1 if health, 2 0 if electronics, and X3 is going to be, oh, sorry, 1 if oil, 0 if electronics. Okay, and then we have 2 interaction terms between the models, which are represented by beta 3 and beta 4. But these are the definitions of the main variables that are in the model, and then we also have a couple of interactions. So the first thing that we have to establish is that we understand that these are categorical variables. We have 3 levels with the categorical variable, which means that we have to create 2 dummy variables because we always use k minus 1 dummies, where k represents the number of levels in the variable. Right? So does this make sense so far? Okay, so we are working up to 3F. All right, so state the reference level, that's electronics. For the data set, the MSE is equal to this, the SST is equal to this, build a regression ANOVA table. So this is pretty much the same thing that we just saw. We just have a more complicated model. Model utility test. Using the same reference level stated in B, define the categorical or dummy variables and propose a straight line model for this data set that does not include interaction terms. Okay, so the model in E is probably what we need. At the 5%, does an extra square stuff give the yeah, okay. So in part, this is our full model in A that includes interaction. In part B, we are setting up the model that does not include interaction terms. So that's going to be a reduced model of the following form, where X1, X2, and X3 have the exact same definitions. But this model just does not include interaction, okay? So now in part F, we have at the 5% significance level, does an extra sum of square F test give evidence that the MLR model with both interaction terms is required compared to the MLR model without interaction terms if the SSE for the MLR model without is 88.690? All right, so we have two models. We have the full model and we have the reduced model. The full model is the model with interaction terms. And the reduced model is the model without interaction term. All right. I'm just going to move this over. Okay, so we want to run an extra sum of squares F test to compare the two models. So starting on step 1, we have H0, the reduced model is adequate versus HA, the full model is required. Okay, on step 2, we have our significance level, which is 0.05. All right, on step 3, we have our test statistic, which is going to be the sum of squares error for the reduced minus the sum of squares error for the full divided by the DF error for the, I need to check this one. This one, I never can remember this formula for some reason. Reduced full, reduced minus the DFE for the full divided by the SSE for the full divided by the DFE for the full. Okay. All right, so we need to work out a few different values for this test. Now, in the question, it tells us SSE for the model without interaction is 88.690. Okay, so SSE reduced is equal to 88.690. Okay, now in part C, we are asked to construct a regression ANOVA table. So we actually need the solution from C or most of part C in order to complete part F. Because in part C, this is where we would work out our sum of squares error for the full. Okay, so I'm just going to write from C, we would have source regression error total right? We would have df sum of square mean square f. Okay, and then these things here are going to be added together. Okay, now part C tells us the MSE is 6.438. Okay, and it tells us the SST is 244.537. Okay. All right, so we also need, okay, we have 19 stock portfolios. So little n is equal to 19. So this is going to be 18 right here. And then, sorry, this is, okay, sorry. Is everyone with me so far? What I'm doing right now is I'm just working out the sum of square error for the full model because we need that. We have reduced, we need full, and then we can get the degrees of freedom. Any questions? Okay. All right, so our full model has 1, 2, 3, 4, 5 explanatory terms in it. Okay, so our regression DF is going to be 5. That means that our error DF is going to be 13, which means that our sum of squares error is going to be 13 times 6.438, which is 83.694. Okay, so SSE full equals 83.694. All right, so now we can continue here. So we have F is equal to 88.690 minus 83.694 divided by. Now notice that we have DF reduced minus DF full. This is just the difference in the number of explanatory terms or the number of coefficients in the two models. So our first model has 5 terms, our reduced model has 3 terms. So the difference in their degrees of freedom is going to be 2. And then we're just going to divide by what is actually just the MSE for the full model. So this is going to be 83.694 divided by 13. Okay, does that make sense? Any questions? Okay, and then this is going to give us an F value of 0.388. And then from this point forward, we're just working through the test. So it's pretty obvious. Well, it should be. So the p-value here is going to be greater than 0.1, right? I mean, a F value this close to 0 is definitely not going to give us anything that's significant. If we wanted to check this, okay, we could go to our F table. So we're going to use, I might as well just write it out. Okay, so we have F equals 0.388. Okay, so we have 2 and 13 degrees of freedom for this to F-test. So we're just using the DF from the test statistic. So we would look for the F table that has 2 and 13 associated with it. 2. Okay, and we're testing at the 5% significance level. Oh, I don't need to do that. Okay, so we have 2 and 13 here. So we're working with this block of numbers. You can see that our F statistic is smaller than the smallest listed value, which means that our p-value must be greater than 0.1. Okay, so here we have so the p-value is equal to the probability that a chi-square exceeds 0.388. Since the probability that a chi-square exceeds 0.388 is greater than 0.1, then the p-value is greater than 0.1. Okay, so then on step 5, we do not reject H0. And then on step 6, we would just say at the 5% significance level, the data do not provide sufficient evidence that the full model is required. Okay, those were good questions. Those were actually the things that I wanted to go over today, so that's helpful. Does anyone, do you have any follow-up questions? Are there any other questions regarding this or some other material?
I just have a question about the final itself.
Yep.
Roughly how many questions are going to be on it?
Yeah, I don't know yet. The other day in the lecture, I gave an estimate based off of the previous midterm. So it was, I forget exactly what it was. It was something like 8 total questions or 7 total questions, but then there was a bunch of subparts attached. So yeah,
Okay.
if you watch the video from Friday, I discuss it in that video, but I haven't written the final yet, so I don't have an exact number for you.
Okay, thank you.
Yeah. Any other questions? I just want to confirm it's at 1 p.m. Yeah, let's confirm that. I'm 98% confident it's at 1 p.m., but one sec, I'll just open up PeopleSoft here, the fastest program in the world. Yeah, Wednesday, April 14th at 1 p.m. to 4 p.m. Yeah. Is it calculation heavy? It'll be the same style as the quizzes. So I'm not going to be asking you to compute a sum of squares by hand, for example, but calculations like what you've seen here, F, ANOVA tables, that kind of thing, you can expect. So I guess it depends on what you mean by calculation heavy. Any other questions? We don't get 10 minutes to upload. You have to submit everything by 4 p.m. The test will be sent out at 12:50. Everything has to be in by 4. So that's, I guess, yeah, that's how it's going to run. Yeah. But ideally, it won't take you the 3 full hours to complete the test. I'm certainly not writing it with that that kind of time frame in mind. Any other questions? Yeah, I said you can definitely. I believe what I said. I don't want to misquote myself. You can expect a question from each of the regression units. So from lecture set 12 and 13, because we didn't get quizzed on that. And then, so those are from the lecture sets. And then from the additional units, you can expect like at least one question. It's not going to be one question necessarily per unit, but you will get tested on something from the ANOVA unit, something from the non-parametrics, something from the first unit, but there might even be like 2 non-parametric tests in there, for example. At least one from each unit, including an SLR and an MLR. Yeah. Any other questions? Yeah, so in quiz number 2, you had to compute SST and SSTR. That's true, but you didn't have to do them using the formula, like the computing formulas. You could do them using the types of calculations that we saw examples of today. So basically just addition, subtraction, and multiplication. So you can expect to have an incomplete ANOVA. Well, you could potentially be given an incomplete ANOVA table and be asked to fill in the table based off of a couple of values, but that wouldn't require strenuous calculation. It would just require using the properties of the ANOVA table, like the examples that we did in lecture today. And that's the same for quiz 2. Quiz 2 did not require you to use the computing formulas. It just required you to use the properties of the ANOVA table. Do you guys want to go over anything else from the practice problems? These were, as I said, those were the main things I actually wanted to cover, was the categorical variable, the interaction between them, and then the extra sum of squares test. So those are the extra things that I wanted to get done anyways, which is great. We still have 10 minutes, so maybe what I'll do is I'll just say, like, I'll just say that in closing that I hope that you guys had a good semester, and I hope that despite the the difficulties with online learning, that you were able to take some positives from this class and you were able to gain some practical skills going forward. I know that for a lot of you, well, a good proportion of you, this is a required course for your psychology program. So I know that from working with psychologists at MacEwan that a lot of this material is used later on. So for example, I worked with Dr. Trevor Hamilton a couple of times, and we were using, Kruskal-Wallis test and two-way ANOVAs and these kind of procedures. So this is translatable to what you actually will do if you continue on in that program. But it's also useful for a variety of other programs too. I don't want to just single out psychology. But yeah, I hope you guys were able to take something from this class. Hopefully in the fall, you'll be back into an in-person learning environment, but time will tell with the way things are going, right? So I will hang around until the end of lecture today if you have any questions. And if you have any questions before Wednesday's final, I know it's sneaking up on us pretty fast here. Don't hesitate to email me, or if you want to set up a meeting, I'll do my very best to accommodate you in the next couple of days. I'll send out some details regarding the final, but it'll run the same way as the quizzes. So that shouldn't be a shock to the system. The only difference is just the duration. And yeah, otherwise have a good luck on all of your exams. I hope you have the best possible summer that you can have, and good luck with your continuing education next year. Okay, so as I said, I'll hang around until the end of the period. If anyone has any questions, feel free to email me if you have any questions. But otherwise, we'll call it goodbye to the lectures, and I'll talk to you guys on Wednesday afternoon for the final.